Here, we'll try to understand and interpret eigenvalues and eigenvectors. Let's begin with a recall, which defines eigenvalues and eigenvectors. A is an n by n square matrix, then an eigenvalue lambda of the matrix and its corresponding eigenvector v are defined as in this equation. AV equals lambda v. The eigenvector v must be non-zero. Consider the matrix transformation. For a matrix, an n by n square matrix, the matrix multiplication produces another vector. The vector y may have different direction and different length from those of x. So the matrix multiplication scales the vector and rotates the vector. However, once the vector is an eigenvector, then it is not rotated, only scaled. Historically, eigenvalues and eigenvectors appeared in the study of quadratic forms and differential equations. In the 18th century, Euler studied the rotational motion of a rigid body and discovered the importance of the principal axis. Later, Lagrange realized that the principal axes were the eigenvectors of inertial matrix. There are two major reasons we need to get eigenvectors and eigenvalues. Principal axis and bases. There are favored directions or favored vectors for square matrices. When the matrix acts on these favored vectors, the action results in scaling the vectors with a rotation. These favored vectors are the eigenvectors, and the scaling factor is the eigenvalue. In many interesting applications, the eigenvectors form a basis, which makes matrix methods and algorithms much more effective and useful. See this example. A is an n by n square matrix, and we assume its eigenvectors v1 to vn form a basis for Rn, and a vi is lambda I vi. Then, for an arbitrary vector x in Rn, it can be expressed as a linear combination of eigenvectors. This is summation notation. If we multiply A, then A can be multiplied to each eigenvector, and AVI is the same as lambda I vi, so we have this term. If we multiply A k times, then we can have here lambda I to the k. This formulation is applicable for many tasks in scientific computing. For example, if A is an iteration matrix, then we can analyze a convergence of the iterative procedures. In many ways, it can be used. Now we consider a geometric interpretation of eigenvalues and eigenvectors. We start with this simple matrix, 2 by 2 matrix, 2 minus 1, minus 1 and 2. Then its eigenvalues and eigenvectors are here. The large eigenvalue is 3 and smaller one is 1. The corresponding eigenvectors are here v1 minus 1 1, and V2, 1 and 1. Now we'll consider action of the matrix A on the unit circle, the circle of radius 1 centered at the origin. For each point on the circle X, if A is multiplied, then image A will be there. So for every point, if you compute the image, then here we'll get this ellipse. Of course, if you choose points inside, then and all points inside the circle, so we consider disk, then the image of disk will be this solid ellipse. Find the area of the solid ellipse, the image of the unit disk by the action of A. Then we can find the area quite easily from this area of the disk, which is pi, and in one direction is not scaled. The eigenvalue is 1, and in this direction 3 times enlarged, so that the area of this solid ellipse is pi times 3 times 1. That is exactly this one, pi times lambda 1, lambda 2 absolute value. So we get the final answer, 3 pi. So products of eigenvalues becomes a volume scaling factor. In fact, the product of eigenvalues is the same as the determinant, and which is a volume scaling factor. Now, eigenvalues are giving detailed scale in each principal directions. Here we have singular value decomposition as an application of eigenvalues and eigenvectors. It's quite popular decomposition technique. Now we start with a general shape matrix. A is in Rmn. M is larger than or equal to n. Once so that A is now tall matrix and number of rows is larger. If it is a flat matrix, then we can take a transpose and then we can make a decomposition. Now for the matrix, we have U sigma V transpose decomposition. U has the same shape as A and satisfying this equation. U transpose U is identity, and V is a square matrix satisfying this equation. In this case, we said that it is an orthogonal matrix. And sigma is also a square matrix. In fact, it is a diagonal matrix. And having entries, sigma 1 to sigma n, and is descending magnitude. Okay, here we have some detail for the decomposition. The singular values are the square root of eigenvalues of A transpose A. And first we get eigenvalues and eigenvectors of A transpose A and take a square root to get the singular value. And collection of these singular values will make the diagonal matrix sigma. Write singular vectors, and V is the collection of eigenvectors of A transpose A. So we collect these eigenvectors to form the right singular vectors. And the left singular vectors, U is the collection of UJs, and UJs can be obtained through this one. here AB, or it's the same as U sigma from the decomposition. Here we multiply V right side, then it will become AB, and then that one is U sigma. This is the principal components. Each column of AV or U sigma is a principal component, and it is forming an orthogonal the basis, in so that we can explore the new the space, and we can deal with sometimes the data very effectively. And also we can make some good approximation through data compression. Okay. Now for a singular value decomposition, and it can be expressed as in this summation. In this case, it's called dyadic decomposition. So the summation is from 1 to n. Now each one is a rank 1 metric. This is outer product, UJ, VJ transpose. And in data compression, and we may try to get the summation up to k, and from k plus 1, we try to discard. Then this portion is called AK. Then mathematically we can prove that the difference between A and AK measured with L2 norm becomes sigma k plus 1. So that when you see singular values, so the singular values are decreasing rapidly, and sigma k plus 1 is small enough, then you are taking only first k terms to get approximation, then the difference is very small. In this way, by taking only very small k components, we can save the data in an approximated one quite effectively. Rather than whole data set, we may try to save in this way much more effectively. This is the idea of data compression. The singular value decomposition plays crucial roles in various applications, including regression analysis and principal component analysis. Now, I hope you understand why we need eigenvalues and eigenvectors, and also some geometric interpretation of them. Okay, thank you.